So we start the afternoon session. We will start with, we're going to talk about negative conduct. 30 minutes.
Okay. Good morning, everyone. I'm LDGianni, and I'm doing a PhD. Yes, I'm doing a PhD in CA. And today I will talk to you about an analysis of trap electron modes instabilities in negative triangularity plasmas. Let me jump directly to the introduction. You had most of it already this morning, but I will say some few things. Yet, do we have a pointer or? Otherwise, I point with like this. Ah, okay.
Ça, c'est bon.
Okay. So, as you might all know already, in tokamak, confinement is achieved through magnetic field. So basically, we have the magnetic field lines and the charged particles drawing helical paths around the magnetic field lines. As you can see here, the motion of those particles can be decoupled in two motions: the cyclotron motion, which is the motion of circling around the magnetic field lines, and the motion of the guiding center of the particle, which in first approximation follows the magnetic field lines. This is the mechanism leading to confinement. Magnetic field lines are wounded on tori called the magnetic surfaces with constant density and temperature nested one in another. And we used to describe tokamak the usual toroidal coordinates, and in particular, the poloidal coordinate is the one circling around the cross-section of the source, and the radial coordinate is labeling the magnetic surfaces, so all nested one in another. Confinement is not perfect, and it is ruled mainly by two phenomena: collisions and instabilities. Those two phenomena lead a radial transport of energy and particles, and the quantity, the figure of merit measuring the goodness of confinement is the so-called energy confinement time, which is at the denominator of this formula here, which measure the time needed for all the energy in the tokamak to leak out. It's okay.
Just
in order to get a net energy production from fusion, which we want to do, we need the density of the plasma multiplied by the energy confinement time to be higher than a certain function of the temperature. We can increase the density up to a certain limit, as you might have seen from some talks last week. And indeed, you can understand that increasing the energy confinement time is crucial for harnessing fusion energy. In the late 80s, people started thinking, let's try to change the plasma shape and see if the energy confinement time is increased or not. Changing the plasma shape, as you saw this morning, means changing the shape of the cross-section of the tokamak. In particular, this is parameterized by two parameters: elongation, kappa, and triangularity, delta. I don't give you the detail of the definition of those parameters because they could be quite technical, so just I would like to give you a visual interpretation. You have a circular cross-section where delta is equal to 0 and kappa equal to 1. You have an elliptical one, an elliptical one here, when delta is equal to 0 and kappa is higher than 1. You have a D-shaped configuration when delta is higher than 0 and kappa higher than 1. This configuration is called positive triangularity configuration. And you have a negative triangularity configuration, which is a reversed D-shape, when delta is lower than 0 and kappa is higher than 1. In particular, today we focused on negative triangularity plasma because it has been discovered that indeed changing the shape to a negative triangularity 1 improves confinement. As you saw already this morning, ITER will operate in high confinement mode configuration, which is a configuration of very good confinement, which is achieved above a certain power threshold, a certain threshold of power injected into the plasma. This configuration is very good, but it is at the same time prone to edge instabilities and other issues. Negative triangularity plasma have the capability to get to H mode confinement level, even staying in L mode, in low confinement mode, so not doing the transition to high confinement mode. This prevent the rate of edge instabilities. And here I just would like to show you two configurations, positive and negative triangularity ones, which are one flipped with respect to the other, where I introduce also the notation PT for positive triangularity and NT for negative triangularity, which you will see a lot during the talk. Why confinement is better? Confinement is better because transport is lower in negative triangularity with respect to positive triangularity plasma. If in fact we write an effective diffusion equation for the heat, here this is density, this is the ineffective diffusion coefficient, and the gradient of the temperature. We measure the diffusion coefficient, they measure the diffusion coefficient in the negative triangularity against positive triangularity plasma, and they saw that the diffusion coefficient is lower in negative triangularity with respect to positive one, even for the same range of parameters. Transport is dominated by microinstabilities, which are driven unstable from strong density or temperature gradients. Therefore, how we can interpret the fact that the transport is lower? We can interpret it saying that in the electron channel, negative triangularity has a stabilizing role with respect to the instabilities, the microinstabilities we were talking about. Here you can see, just to give you an interpretation, a visualization on this, you can see from experiment on TCV that the perturbation of the temperature plotted for positive triangularity plasma and negative triangularity ones as a function of the temperature gradient. You can see that positive triangularity ones have a higher plasma have a higher perturbation between the two negative triangularity plasmas, even for the same gradient, so the same drive of this stability. In the electron channel, we will focus today on the electron channel. In the electron channel, the main responsible for the heat and dark particle transports are trapped electron modes. Sorry for the jargon here. I will just introduce in the next slide what trapped electron modes are. So this will be much more clear just in few slides. We have to say that this situation has been confirmed also in other turbulent regimes, not a thing just related to trapped electron modes, but here we will study trapped electron modes. In order to understand what trapped electron modes are, we have to see before what trapped electrons are, what trapped particles are. In a tokamak, particles have a certain momentum mu and live in an homogeneous magnetic field. The momentum mu is conserved and it is related to the perpendicular velocity of the particles. An homogeneous magnetic field means that the magnetic field decreases with radius here, as you can see here, with the major radius of the tokamak. If we write the equation of motion along a field line of a particle, we see that the particle feels a force which is proportional to the momentum, and the gradient of the magnetic field along the field line L. The total energy is conserved. You will understand then that there will be some particles with an initial velocity which will be not enough to raise up the magnetic well. Those particles will be stopped by the force, and at a certain point they will be stopped, and they will be forced to bounce back and forth into 2 points in the magnetic well. Those particles are called trapped particles and have a typical trajectory, which has a banana shape, so it's called a banana trajectory. Trapped electrons have some characteristic frequencies that are very important for the motion, for characterizing trapped electron modes. One of them is the bounce frequency, which is called omega b, and it is the frequency of bouncing back and forth of the particles along the banana trajectory. So they will bounce back and forth and with a certain typical frequency omega b. Then another frequency is omega d, which is called precession frequency, and it is related to drifts of the particles into the toroidal direction, because those particles drift in the toroidal direction and with a certain frequency, omega d. And omega b, so bounce frequency, is higher with respect to omega d. Furthermore, they are characterized by a last frequency, which is a diamagnetic frequency. This is a frequency related to collective drifts due to temperature and density gradients and to pressure gradients. The instability of trapped electron modes arises when the electrostatic perturbation, so a perturbation of the electrostatic field, enter in resonant interaction with the toroidal precession frequency, so with this frequency here. An important characteristic of microstabilities in general, but also of trapped electron modes, is the ballooning characteristic. It means that the instability is much more localized into the external part of the cross-section with respect to the internal part. Here I'm showing you a delta P, so a perturbation of the electrostatic potential for non-active symmetric modes from a simulation, a Gisela simulation, so from a gyrokinetic code named Gisela, where we see clearly the ballooning aspect of the stability. So the fact that it is much more localized in the external part of the cross-section of the atoms. An important thing to be noticed here is the fact that those frequencies depend on geometry. So depend on whether we have a negative triangularity plasma or a positive one, not only, also on elongation or other parameters, but here we will just compare positive and negative to do the simple. They depend on geometry in this way. If we plot omega d, so the precession frequency, which is the drive of the stability, so we don't have to forget that it is the drive of the stability, so we are particularly interested in this quantity. If we plot omega d as a function of theta b, where theta b is the bouncing angle of the particle, which is the maximum angle that the particle draws in its banana trajectory, we see that it has different shapes for positive and for negative triangularity, different shapes as a function of theta b. In particular, in this area, in this region here, of small theta b, where the particles are because they are the particles much more trapped into the magnetic well, into the region of low magnetic field, positive triangular omega d for positive triangularity is higher with respect to negative triangularity. Instead, in this region here of high theta b, so in the region of the particles drawing almost the whole toroidal trajectory before bouncing back, where the particles are called barely trapped, negative triangularity omega d is higher with respect to positive triangularity 1. So what we can say about this omega d is that for negative triangularity plasmas is lower than for positive 1 in the region of deeply trapped particles. Ah, okay.
You might say it's trapped.
The image. Yes, yes, will be counted. Will be? Yes, yes.
Sorry. Let me see if okay, yeah, it works. With? I will. Let me see. If I do this and this, okay, follows.
Okay, so now I introduced all the concepts needed in order to understand what we did. And so let me jump into our work. We are interested in Capelletto modes because they are fundamental to explain stabilization of negative triangularity, to explain the better confinement of negative triangularity plasma. Furthermore, they are important in fusion because electron heating is commonly used, energetic ions heat electrons, and in a fusion reactor, the temperature of electrons will be either higher or the same of the temperature of the ions. In all this picture, all this framework, our goal is to understand the physical mechanism for stabilization of Capelletto modes in negative triangularity for extrapolation towards reactor-relevant configurations. In order to achieve this, we use a double approach. The first one is a reduced model, which is interesting because it allows us to scan a broad range of parameters and gives us the possibility to grasp a physical understanding, to have a physical understanding of the basic physics behind, of the key parameters playing behind the stabilization in the negative triangularity. And it is a linear model. But nonlinear physics is very important in negative triangularity stabilization. Therefore, we run nonlinear gyrokinetic simulations with the global code full F Gisela. Just few parameters I will use. Sorry, it's a long introduction, but needed. A few parameters I will use from now on. The safety factor is a parameter, plasma parameter related to the helicity of the magnetic field. So magnetic fields have some helicity, and the safety factor measures the toroidal turn that the magnetic field line does with respect to the poloidal turns. The magnetic shear is the shear of this quantity. The aspect ratio is the ratio between the big radius of the tokamak, so this one, when it comes magnetic axis up to the cross section, and the radius of the cross section of the torus itself. So here you can see a small aspect ratio tokamak, also known as spherical ones, and the large aspect ratio tokamak, which is similar to tokamak that we have nowadays. And last but not least, elongation and triangularity, which I already used. So we wrote a reduced models through a linear analysis. We coupled the Vlasov equation to the quasi-neutrality equation. We used the analytic equilibrium and
sorry, this is not. I think the.
No, the slides I think have been messed up at the second point because this should not be here and yeah, that's okay. Let's and the dispersion we thanks to the Vlasov equation and the quasi-neutrality equation, we get to a dispersion relation, which is the sum of different terms. One is an adiabatic contribution. The second one is a Capelletto contribution that of course will be very important. And the third one is a passing ion contribution. We solve the dispersion relation in order to get the frequencies of the modes, where we are particularly interested in the imaginary part of the frequency because it represents the growth rate of the mode. So of course we want to see if the modes grow more for positive triangularity or for negative triangularity. I will detail very briefly what inside those contributions, inside this dispersion relation. First of all, trap electron contribution, it is the most important. it is a double integral on the bouncing angle and the energy of the particles. The drives of the stability, you can see there, them in red, they are the diamagnetic frequencies, so the temperature gradient and density gradient. The resonant contribution between the mode, which is the frequency of the mode, and the precession frequency, you can see here, resonant contribution, and the bounce frequency. A very important piece in this equation is this W function here. You don't need to know what this function, how this function looks like. I put it here, but it's not very important. The important thing is that physically it represents the ballooning of the stability, where the ballooning, I recall, is the property of the stability to be localized in the external part of the tokamak, of the cross section of the tokamak. All those quantities here are function of shaping, so will be different depending on shaping. The passing ion contribution, then we added this contribution because in the beginning we didn't have it, but then we added it because we understood that it was quite important to recover the physics, to have all the physics ingredients needed to recover the good grow rate. We have here again an integral on the theta angle, so on the same angle as before. This is the ballooning contribution. It's written a bit differently, sorry, but it's a matter of mathematical reworking of the things. In the denominator, you will notice that there is no resonance differently from what it was for electrons. And this is because we didn't want to include also resonant interaction of ions. And we have an operator for finite Larmor radius effects. These finite Larmor radius effects are given by the fact that ions Larmor radius, which is the radius of the cyclotron motion around the magnetic field lines, is much bigger with respect to the electron one. So since we are looking at particles here, not a gyro center, we need to take into account the Larmor radius for ions. For electrons, we don't need because it's very small. This quantity here, so the finite Larmor radius operator, is a function of shaping as well. Where this AS, this quantity here is a bit technical, is the derivative of the field line with respect to the angle theta. Finite Larmor radius effects are stabilizing for trapezoid stabilities, increase with the Kperk, which is the perpendicular wave number of the mode, and increase with the magnetic shear S. The magnetic shear is the shear of the safety factor. In order to understand whether or not we included all the physics needed into the model, we benchmarked it with a well-established gyrokinetic local code, local and linear code, which is called GIN. Here you see the grow rate of the stability is a function of the poloidal wave number, normalized with respect to the Larmor radius. This is not important. For two values of shear, for positive and negative triangularity, and with the same for GIN, and with the same range of parameters, our theoretical results, so the results we got from the analytical model. And you see that qualitatively they match. In particular, we see that positive triangularity is less stable than negative one. So negative triangularity is more stable than positive one, same as for GIN. And also that we see that increasing the shear, we have a stabilizing effect. So we recover the trend, even though we don't have a good quantitative agreement, but this was not the object, because of course it's a reduced model, it's not a gyrokinetic code. We have a good qualitative agreement, and also we have the same order of magnitude of the grow rate, which is TM only, pure TM. Yes, so we didn't include ITG in the model. Okay. Okay. What we learned on physics here. We learned from this model, we learned that ballooning is crucial for stabilization of negative triangularity. In particular, if we plot the power given by the electrons to the electrostatic field, so the power feeding the stability, as a function of the energy of the particles and of the angle theta b, so the bouncing angle, where the positive one, so the yellow one, means that the energy are giving, the electrons are giving energy to the stability, we see that if without ballooning, this energy is spread all along theta b, is spread all along the bouncing angle. And in this case, what we found with the analytical model is that negative triangularity is more unstable with respect to positive one. This was not expected. And what this means is that if the energy is distributed between deeply and barely trapped electrons, negative triangularity will be less stable than positive triangularity. If instead we include ballooning, we take into account ballooning, as we did in the end, the power, we plot the same quantity, we see that the power is much more localized in the area of low theta b, low bouncing angle, which is the area of deeply trapped electrons, as I told you. So basically, in this case, what you get is the inverse trend, and it's a good trend, the trend for which negative triangularity is more stable with respect to positive one. This means that if the energy on deeply trapped electrons, negative triangularity is more stable indeed than positive triangularity. This points towards the fact that deeply trapped electrons are quite important for negative triangularity stabilization. We can give a physical interpretation of all of this. The picture I showed you of omega d as a function of theta b without ballooning shows that for deeply trapped electrons, the positive triangularity has an omega d which is higher with respect to negative triangularity for deeply trapped electrons. When we include ballooning, we see that it is given much more weight to deeply trapped electrons with respect to barely trapped electrons. And so positive triangularity omega d get enhanced by ballooning. And in particular, we can notice the fact that here the integral of omega d over theta b is higher for negative triangularity than for positive. Here instead, with ballooning, the situation is opposite. The integral is higher for positive than for negative. Far from instability, we can model this far from resonance, so far from gamma equals 0. We can, oh, again.
Yeah, I get it. I don't know why. I'm sorry.
I get the minutes more when. No, even more.
Sorry. Well, it has worked an entire week before. That's
Okay, I think it's okay now. Okay. So I was saying that if we model this stability far from threshold, so a very high growth rate, we can model it fluidly. So through a fluid, we can use a fluid model to model this stability far from the resonance. And so we model it as an interchange stability, and if we do so, we see that the growth rates are indeed proportional to the integral of omega d over the bouncing angle theta b. So this appears quite clear now. We enhance, thanks to ballooning, the response of deeply trapped, which are favorable for negative triangularity, and therefore the integral of omega d gets higher for positive triangularity than negative triangularity, and we recover the good trend. this analytical model is quite interesting because it's giving us the possibility to scan a broad parameter range. Here you can see two examples. We can, in a few time, in very, very few hours, you can see that delta, so the triangularity from negative to positive, as a function, and the shear. So you see the growth rate as a function of delta and the shear, and you see that indeed we recover a quite not obvious trend here, which is recovered indeed by gyrokinetic simulations as well. And for the same thing for the aspect ratio, here the trend is a bit more monotonic, but okay, we recovered the good trend even here. So the reduced model is both made, and the thing important thing is that we can explain all those trends here because we can switch on and off the parameters, and we can switch on and off the physical key parameters and see whether are these parameters or the other one which is giving the trends. Here, I'm not detailing it for reasons of time, but we have a physical understanding of the trends, and we use this framework to guide us for choosing Gisela simulations parameters, because Gisela is a full F global code, which is quite heavy to run, so we need a guide for choosing the parameters before running a nonlinear simulation. Okay, now I will talk a bit more about Gisela simulation, so nonlinear simulation. Indeed, you saw that linear physics give the right trend, so give the negative triangularity is more stable than positive, but still quantitatively we are not that happy because we think that quantitatively those trends are not enough to recover the trends for the observed into experiments. So we think that some self-organization mechanisms are playing a role here, some nonlinear mechanisms are playing a role, which give some energy, can give some energy to large scale flows, which can be beneficial for compiling. An obvious like candidate for these are zone flows, which have been already studied in negative and positive triangularity. But zone flows have the characteristic of not being that much effective for turbulence regulation in TM's computations. But some studies show that we can find a region of the parameter space where zonal flows are supposed to be effective for turbulence regulation. In particular, here I show you a plot where there are the temperature gradients as a function of the density gradients. Here, this region here is a region where trap modes are unstable, so are playing a role into turbulence. And in this region, we have a certain probability to find effectiveness of zonal flows in turbulent regulation by TM. So we put ourselves here in this parameter, in this region to have the maximum probability. And we have some small collision. Linearly, in this regime, in this parameter space, linearly we observe a similar behavior of negative triangularity and positive triangularity, which is opposite to what I told you before, but it's of course parameter dependent. So in this parameter space, that's what we observed both in Gisela simulation and in the analytical model. The state of the art for the nonlinear phase, so we get up to the nonlinear phase, and here you see the turbulent flux, an example of turbulent flux in this simulation, as a function of time and the radius, the small radius of the document. And you see here the linear phase where gams are dominant, and then here the nonlinear phase starts. So we are in the beginning of the nonlinear phase. But still, we do some nonlinear considerations. We don't have a very clear picture nonlinearly with a similar drive, which means with similar density gradients, because the drive here is density in this simulation. So with similar density gradients, we get fluctuations lower in negative triangularity than positive triangularity. Here I'm plotting the fluctuation of the electrostatic potential, the RMS. And we see that in positive triangularity is higher, fluctuations are higher with respect to -1. Furthermore, turbulent autocorrelation time is higher in negative triangularity than positive. Here I plot the autocorrelation function and as a function of time, and we see that for negative triangularity the time is slightly higher. And if I plot the 2D maps of the perturbation of the electrostatic field in positive and negative, we can see here, maybe it's not that much clear from the projector, but we see that the turbulent autocorrelation length is shorter in negative with respect to positive triangularity. So all of these made us think of an effect of zone of flows. We looked at the shear of the flows, and we look in particular, we use, in order to compare positive and negative, so the effectiveness of this shear, we use the figure of merit, which is the equals the shear multiplied by the autocorrelation time, mediated averaged on time, of course. And we see that it is slightly higher in negative than positive triangularity. But if we don't multiply by the autocorrelation time, so if we just look at the absolute value, it's kind of similar. Furthermore, we have, if we look at the effective particle diffusion coefficients, so if we divide the turbulent particle flux by the density gradient, so the drive of its stability, and we compare negative and positive triangularity in the electron channel as a function of the radius, we see that the negative triangularity diffusion, particle diffusion coefficient is higher with respect to the positive one. So the similar situation for electrons, and this is a bit surprising to us for electron effective heat diffusion coefficient. So we look at particles and heat, and it is a bit surprising to us since we observe the higher fluctuations in positive with respect to negative. So seems to be a bit this in contradiction. It could be explained by a phase difference between the density and the electrostatic field. Indeed, the turbulent particle flux can be written as a sum on the Fourier space of a density, electrostatic field, and a sinus term, which includes a phase difference between density and electrostatic field. So maybe these phase difference might play a role in a higher transport in negative with respect to positive triangularity. So in conclusion, we played with the analytical model, seeing that precession frequency is a key player in linear stabilization of trapped electron modes by negative triangularity. But only if accounting for the ballooning property of the stability. We find a good qualitative match with gene local simulations, and we scan the parameter space to get insight on the role of parameters. Even if the growth rates of negative triangularity are lower than the growth rates of positive triangularities, differences are quite small. So we think that non-linearly we will find something. For the moment, in the region of the parameter space where we put ourselves, which is the region which is supposed to have the higher zone of flow activity, trapped electron modes do not seem to be stabilized much by negative triangularity, but some turbulence property need to be further analyzed, and moreover, simulations need to be continued. Thank you.